Welcome to Careless Coder, and today we will continue our ARM64 assembly on Linux. We will be creating a method that allows to print us a hexadecimal value to the screen, which will cover the logical shift right and logical shift left. Two very important opcodes that you will use in pretty much every assembler all the time. So let's jump in and have some fun. Okay, we start off with the code that we did last time. If you have not seen last time's video, printing decimal numbers to the screen, watch that video first. We're going to build upon that knowledge. We're doing a bit different than I would usually do. Usually I would use the stack like we did with print decimal. Since we already done that, I think let's do it a little bit different. Usually start on the lowest nibble, mask that off, put it on the stack, shift right 4 nibbles, mask that off, put it on the stack, and that way when you print the stack in reverse you have your hexadecimal number. That's the logical way to do this. We are actually going to do it a little bit different. We're going to mask the top nibble. I'm going to demonstrate this with a 16-bit number because I'm not really wanting to type 64 bits for demonstration purposes. Let's take a random number. We're first going to mask off the top nibble with a logical end. And 1, 1, 1, 1. 1, 2, 3, 4. Now obviously you will know that everything that is a 0 that will be set to 0. If you have done your computer science. So we are left with the top nibble. We're going to use that actually as an offset in a character array from 0 to 9 in an A, B, C, D, E, F. But since it is in the top of a 64-bit nibble, that offset would be humongous and we don't even have that much memory. So then we need to logical shift it to the right, and that is the total number of bits minus 4. So in our case 16 bits, it will be right shift 12 bits. We have 13, that's indeed that. And we're going to use that 13 as an offset in a character array, a hexadecimal character array, and we're going to print that to the screen. So let's first create a character array. Let's call it hex array. Dot ASCII 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F. Okay. And now already create a print uint. Let's change this into hex. And let's also change the string with a nice hex leader 0x. Okay. And let's now create the print hex function. First thing we always do, store all the registers you're going to use onto the stack, starting with the frame pointer and the stack pointer. If you don't know what I'm doing here, I refer you again to last fixed video. This is very important, and there we explain it. I don't quite need that many. Yes, I do need that. And as I say, as soon as you start to push things on the stack, immediately in your code undo it, because otherwise you forget it, you're bound to forget it, and you're screwed. Add back the 0. Okay, and we can return from the branch link. So we have all our registers nice and safe. Now we can start to make some code. Let's use x3 as our nibble counter. Let's make it a bit more optimized. Let's use w3. The reason that you should use w instead of x for performance reasons is that x requires the system to transfer 64 bits over the memory bus. And depending on your SOC, your memory bus is perhaps only 32 bits wide. so it needs to read twice as much. So you would utilize your memory bus far more than you actually need, so optimize that. Let's start implementing the print hex mask part. So first, what I demonstrated is we're going to mask. Let's put that result in x5, and the value that we're going to print is in x0. And we need to mask off the top 64 bits. This is the reason why you tend to use the lowest. So let's do it like that. Mask top 4 bits. Okay, then we said we're going to shift those all the way to the bottom. So logical shift right, x5, x5, and we have a 64-bit system, but we already want to keep the 4 bits, so we're going to move it 60 bits. And we're going to shift up the value that is in x0, 4 bits, so we have the next 4 bits in the most significant nibble. So logical shift left, x0, x0, 4 bits. Now let me show you on the calculator what logical shift left does. For example, we have a 16-bit system and we hold this number. And we're going to shift 4 bits to the left. What that does is actually pushes in 4 zeros and shifts everything to the right. If it is a 16-bit register, this top nibble doesn't fit anymore, so it falls off. Let's do that. Left shift 4 positions, binary. So you see that top nibble is now shifted all the way to the left. If your register cannot hold that anymore, it will disappear in oblivion and the carry will be set. And you see that the next nibble is now in the most significant nibble. Opposite, if you have rotate right, that is also a function. What it actually does, what is shifted off, gets in the carry and introduced back in the back. So you could actually, in our logic, shift 16 times, rotate 60 times to the left, roll, and then still be working, and you end up with the actual value in x0. Logical shift left is actually the same as multiplying by 2. Logical shift left 1 is multiplying by 2. Logical shift right is basically dividing by a multiple of 2. I hope that makes clear, but logical shift left, logical shift right, you will use a lot. So now we can actually increment our nibble counter, because we need to know when to stop, and we need to stop when we have 16 nibbles set. And otherwise we actually have a value in here that we can now print. So let's do the print. Let's mark it also as the hex print, so we know what we're actually dealing with. We're first going to load x1 with the pointer to our hex array. Then we're going to use the x5 as an offset. So we're going to load a byte from that hex array. We put that in W5. We want to keep that in 5 because 5 keeps the value already, so there's no reason to introduce a new register. From where x1 is pointing, the offset x5. So if x5 contains 13, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, D. So then W5 will now hold the D character. And now we can actually prepare the print statement. I think the next lesson I will dedicate to making macros, because we keep filling out that same piece of code to set up what we're going to print, the amount of bytes we're going to print, and calling print way too many times. A macro will make that so much easier. And we need to say we're going to print 1 byte again. And then we say let's print. Okay. Compare x3 with 16. If we have not done 16 values, then branch to print hex mask. And if we have done 16 values, then we printed the whole 16 4-bit hexadecimal number and we can return HexPrint. And there we go. Oh, something is wrong. Nothing is printed. Why not? Let's have a look. Print character. Oh, I don't load the character. Store byte, which is in W5 into X1. You were probably already yelling at me, you forget to load X1 with the character. And now we should have it's 0. Why is it 0? Is my value 0? No, my value is 655, so that should be FFF. So there is a little bug here. Let's analyze the code. I'm going to mask that. Top nibble, then I shift it to the right. Yes. We shift for X0 the next nibble in the top. Yeah. Oh. We need to add 1 to the counter. And there we go. But hexadecimal allows us to omit all the leading zeros, and these 16 4-bit hex values are too large to read otherwise, so let's implement that. So basically we're going to need a little flag, move W5, 0. So as long as, in W4. So as long as we have leading zeros, W4 is 0. As soon as we have any other digit than 0, we set this to 1, indicating that we have no longer leading zeros. So let's do that. Yeah, we can do that right after here. So compare W4 with 1. As long as W4 is 0, we continue, but otherwise we can actually print. If it's equal then 1 to 1, we can go and jump to the print logic. And otherwise we need to compare whether W5 is 0. If it is equal, if it is greater than 0, we're going to set a flag. Print hex set flag. Branch greater than BGT, and that is it. And otherwise we compare here if X3 is a W3. We're going to optimize it to now it is 16. We add 1, we compare with 16. So if it's not equal, we continue, and then we're basically continuing with leading zeros. If 16 actually is reached, so we have 16 nibbles set to 0, so X0 is basically 0, then we fall through anyways, and then we print a 0, so even the 0 state is covered. So this should get rid of all the leading zeros. And of course there is an error. Set flag. Set flag. Print hex. Set flag. Oh, we didn't set the flag. That should go here. Print hex. Set flag. Move, which did we use as the flag for? W4 to 1. And there we go. Print hex. So there you go. We got rid of all the leading zeros, which is still a valid hexadecimal number. Let's change that number to 0 to validate whether that logical fall through actually happens, and we still print a 0. Yes, we do. Nice. And let's set value to 256. That should be 100. Yes. Cool, yeah. So we have a working print hex function. So there you have it. We created our own print hex function. We covered logical shift left and logical shift right. You should now have all the knowledge to implement your own print binary function. So do that as sort of a homework exercise. If you're stuck, there is also source code for that in the GitHub, so you can have a little peek. But you should be able to knock that out in about 30 minutes, maybe an hour when you're new to it. So try that, it's a good little exercise. And next time we will cover using macros. So I see you in the next one.